通じちゃうとまずいので、いろんな意味で来るんじゃなかったと思ってるんですけど、社長の話した後はあれかなと思って、もうみんな興味ないのかなとか思いながら登壇しますけど。Let me begin to talk about the introduction to the Epiphany programming. I'm a real researcher in the computer science. So I just introduced myself a little bit. I was working in Portugal about for 8 years. Then I was working for the research to fight with developing interface for the new computing system, that is GPGPU. Because I was working the GPGPU world before the CUDA. So then I was fighting with the NVIDIA and so on then in Portugal. Then when I was staying in Portugal, it was very funny because the J.K. Rowling was living there. And テルマエロマエの方が住んでたりとかですね。当時は非常に面白かったです。I have to talk English and Japanese both. So then I came back from Portugal on 2006 because of the Lehman shock. Because after the Lehman shock, it was very bad environment in Europe. Then I came back from Europe. Then I'm now working in a university in Japan. I just graduated University of Tsukuba, then just come back to University of Tsukuba. So yes. Then I was working in this kind of things. Then I really researcher. So I was working in the fastest network in the cluster. Then I received the Best Paper Award. This is the first cluster computing conference. Now it's very difficult, very top conference. It's very difficult to accept it because even if I send my paper, it's rejected always. So what the first Best Paper Award winner is me. So then this is a cluster computer network. Then I used the IEEE 1394 FireWire. Then I was working with Ono-san. Ono-san どこにいる？I was working with him. Then this work is when I was student. So I want the student in Japan should have this kind of very much motivated. I was motivated very much and working with Mr. Ono. Then I upgraded this technology to this. Then this is a 60.4 gigabps network for the cluster computer like this. Then it was the fastest network in the world on 2006. But now it's 40 gigabps if we use InfiniBand. Then I gave up because it's just like fighting with technological and industrial technological, how can I say this, level. So it's not academic. Then I quit this work. Then I moved to the, I'm sorry, it's in Japanese. I moved to the GPGPU world. Then I was making this kind of very easy programming environment, and I patented in Portugal. Then I moved this idea to Japan. Then I got a very big budget, and I was working for this using a very big budget in Japan. Then after this, this was published in a computer, and so it was very famous in Europe. Then I also writing these. I think you know this one. みんなこれ知ってますよね。僕のこと知ってる方どれぐらいいますいないか？本当ですか？ありがとうございます。ありがとうございます。This is very,ね、I should have wrote the English version this. これすごい売れたんですね。2万部ぐらい出たんですけど、そうそうすごい出たんですよ。で、一時期ですね、これ自慢になっちゃうんですけど、発売当初一番最初の時楽天で40位まで行ったんですよね。そう楽天で40位に入ってるんですよ。おおとか思ってですね。そうあれですよ。全部でですよ。全部で。おおとか思ってですね。そうおおとか思ったんですけど、まあそういうのがありました。で、まあこういうのをやってました。So, okay, using these backgrounds, I bought the Parallella about 1 week and a half, so 2 weeks ago, because my good friend Mr. Miyahara from RS Components asked me, oh, do you want to have a presentation in a conference? I said yes. Then finally decided to say yes. Then which kind of thing should I talk about? I asked to Miyahara, then he said, you are a specialist of the parallelism, so you should talk about the Abatiba's LSI. Then I choose the Epiphany's programming. Then this is, Epiphany is many core architecture. So it's almost the same as GPGPU. So I just talk about this kind of part in the Parallella. Because if you use the Parallella, just a processor, it's a Zinc. So it's a Xilinx Zinc. So it's just an ARM processor. So it's not parallel. But if you use Epiphany, you need some more knowledge about parallel programming. Then I just show some example. Then if you use Epiphany, you need to make two kinds of programs. So this is very traditional since the beginning of GPGPU. The first of all, the host processor controls Epiphany by initializing the system and downloading the program, then initialize the memory, then writing the input data to the Epiphany side. Then the Epiphany will, I missed to put I think there should be the execution of the program on the Epiphany side. Then after the execution, the result will be read by the ARM processor. That is the way to execute the program. Then finally the system, but yeah, just reading the data from as a result of the program. Then what is the architecture of the Epiphany? I just read the manual of the from the Adaptiva about 2-3 days. I understood what is inside, but it's very easy. So it's a very commodity, not commodity. It's a very conventional architecture. It's very understandable. So that is like a mesh, and each cross point of the network have processor. Then each processor is like this. So it's connected like this. The router is pointed in the cross point. That router will communicate with the each processor. Each processor will communicate via these network. Then this network will be connected the outside memory and the connection to the parallel side and so on. Then currently it releases 4x4 or 8x8. Is it correct? 8x8. 8x8, 64, right? Yes. Then it's we say it's 2D mesh topology. If it is 2D mesh topology, it's the network cost is n log n, I think. I think n log n. I think you should check in the parallel computing textbook. Then how to begin the Parallella? It's very easy. Burn the image to the SD card. So then initially DHCP is configured. It was very hard to find this information. It's DHCP is configured, so it's very hard to find this information, but it's DHCP. Then connect to LAN, then try to find the MAC address is beginning from 044F. So it's Parallella. So then they connect terminal like Teratam via SSH and log in by user using the Parallella. So in the beginning, it's very it's the same as the Raspberry Pi. If it is Pi Raspberry, right? So if I connect to the global network in the university, after one night, there are so many attacks by using the same password. So be careful about this. Change the password in the beginning. Then you can find this is the only the beginning. Only in the beginning you can see these messages. After that, it's deleted. So then after that. Epiphany is available from the beginning because the SDK is already installed inside. The latest kernels include the Epiphany SDK, eSDK we say usually, and brown deer. Is it correct pronunciation? Brown deer. Brown deer. I don't know if it is Portuguese. Brown deer. So it should be brown deer. Brown deer. That is a company. Brown deer is making and it's very difficult to pronounce Kopu something SDK. So it's a Parallella SDK. Then that SDK is already downloadable from the internet. It's free. and they say it's open source. Then, and currently available programming methods, there are two methods are available. One is ESDK, that is higher hardwired programming. So there is no support like a standard support like MPI, OpenP, and so on. So you need to write from the scratch by using the SDK. The another one is the this SDK, Parallel SDK, I just say. Parallel SDK, or using the OpenCL framework. The OpenCL is very, I think, do you know, who knows the OpenCL? Ah, OpenCL, yes. Everyone should know, right? So OpenCL. And in the internet, I think you can find the information about MPI. Then I believed, oh, MPI is available in this very small chip. I thought it's very exciting, but but now this library is the version is 1.6. They say from 2 point something it will be available. Then the availability of MPI is in the paper. Paper means nothing. So yeah, okay. So I think someone should work. It's not so difficult. So I think someone should make the MPI, I think. Then I think you can see many news about the MPI is available in the Parallella, but it's that article is saying about the Parallella on the ARM core. So be careful about that. So Parallella on the Epiphany core is not available in general. So then if you use the hardwired programming by using the ESDK, we can use these programming tools. One is, these are just, as you know, just a compiler and server. This is a debugger server that connects to the processor core in the Epiphany. Then reset the system and hardware revision and so on. To check the hardware revision, we can use this command. And e-loader and e-read, e-write seems like a loader to the processor, but it's not a loader, is it, right? So this is just a yes, these are the loader to loading the program to the e-core, and e-read is reading the memory from the Epiphany side, and e-write is writing the memory to the Epiphany side like that. And so we can dispatch the program using these commands by from the command line. Then e-run, be careful about e-run. E-run is just a simulator, so it's not like a command to run a program in the Epiphany side. So these are the tools. Then I just show a small example. 何分経ちましたで、今、あそこで動いてます。The Parallella is running there. I brought the Parallella using my bag that said supercomputer K. Yes. Parallella. Okay. Parallella. But I changed my. Yes. Of course, I changed. I just moved my window. Yes, as you know, you can log in like this. Then, for example, I just show a very easy one. Hardware revision. Hardware revision, right? Hardware revision. This one. Then you can see like this. Then we can check the number of cores using seeing this number. So it says E16, so it has 16 cores. So 4x4 many core processor. Then and Parallella 1 and so on. So using these commands, you can check and you can run the program directly to send the program to the Epiphany side. The another one is this is the flow to execute that one, right? By using the command line. So it's just using the e-loader and e-write and reading and so on. The another one is the program invocation from host program. It's based on the program. In the program, there is in the ESDK, there is a library that executes, how can I say, it invokes that the same activity in the command line. So then it sends どこ行っちゃった？これだ。It has a EasyCC, then we can compile the host program by using the EasyCC, then makes executable by using these steps. The EasyCC is executable in the E-core side. I'm sorry, the executable in the E-core side. This is the like an embedded program in the Epiphany side. It doesn't work in ARM side. Then in the ARM side, there is another program we need to make. So that is GCC, the normal GCC in the ARM side. Then in the ARM side, it programs like a loading ELF to E-core. It's like a loader. So then it sends the program to the Epiphany side. Then the setting up the memory and invokes the ELF, and finally it reads back to the results. So then we have to write the program using by these steps. Then these steps are implemented by the library, this eHow. Then yes, eHow. Then there is an include file like this. そこのヘッダーファイルとこのライブラリ使って、で、こういう関数使えばいいんですけど、the main functions are initialize and finalize, and reset the system, then share mem. Share mem means shared memory between the host side and the Epiphany side. Then we can define the shared memory area by using these functions. Then attach is trying to attach. Attach means just try to get the pointer. ポインターを、Epiphany サイドのポインターを、取るっていう作業をこれします。try to get the pointer from the Epiphany side to the host side. Then host side can access directly to that shared memory. And open close is open the system and closing the system. Then eload is loading the program. When we load the program, be careful about that because the format should be the S format, the Motorola S format. Do you know the Motorola S format? Yeah. So it's not ELF, so it doesn't work if we pass the ELF directly to the function for the loading. So we need to change by using the object copy, I think, object copy command. Then e-reset, e-read and write is reading and writes that this shared memory area. And the Epiphany side, it's very simple. So there are almost the same command, almost the same functions are prepared. One is eGet equal ID. Equal ID, what is equal ID? Equal ID is like a identified number, numbered for each core. So its original number will be returned by using this function. Then the program can know which part that program have to execute in part of the very large algorithm. Then the E-code from core IDs, we can know the coordinate. Coordinate means coordinate っていうのは、座標ですね。だから 4×4 だったら 4×4 のどこにあるかっていうのをこの code from core ID っていうので探せます。で、share mem attach is almost the same. It's just attaching the shared memory area and read and write the shared memory and so on. I will show a very easy example. Is a hello world example. Hello world means just sending the program to one of the core. Then the core will make message by using the original ID. でそれぞれのコアにとりあえずプログラムを送って、プログラムがこのコアが一つ一つのその自分の ID をメッセージとして出してきて、で it will be wrote to the it will be written to the shared memory. Then the shared memory will be read by the ARM core. でそうするとこれ書いてシェアードメモリが読み出すので、それぞれのが書いてくるからみんなで動いてますよっていうのがここに返ってくるはずですよねというのをちょっとデモでやります。I will show a demonstration. はい。はい。で、プログラムとしてはまあ非常に簡単で、It's very easy program. So but just using the reset and get platform and share memory allocation and so on. And open the system. Then this is the important eload hello world.srec and just sending to the Epiphany side, and you sleep. So there is no, I'm sorry, there is no synchronization with the Epiphany side. So it's just waiting for you sleep だから 10 milliseconds, 10 milliseconds. Then just reading the result and print the message from the Epiphany side. Then in the Epiphany side, it just say, just get the get core ID, then just make message by using this core IDs. Then, for example, I am number something, so I am core number something. Then just write that message to the shared memory and just return. Then I just show an example. エピファニー、ハローワールドかなですね。で、there are two kinds of program. One is the これが Epiphany side で、これが、XXXX、どれだホスト。これがthis is host side で、アンダーバーですね。で、so this is just calling each core. So each core has different number, right? So this is a coordinate 1, 0, 1, so it's 16 core. I'm core something. So all the core will return like this. If we use this function and if we make a parallel program using this function, we can make a very large program. で、お時間が押してまいりましたので、次は next is OpenCL. The OpenCL is another way to program a parallel program. The Brown Deer this SDK supports OpenCL based on ARM and Epiphany. And I tried the ARM side; it doesn't work. So I'm not sure what is wrong. And to use ARM, specify CL device type CPU. You can understand, right? So if it is CPU, it returns the ARM side. If you specify the CL device type accelerator, it returns the Epiphany. So of course, we need to specify this one, right? Then I just show an example, the two-dimensional DCT. So it's a 離散コサイン変換ってやつですね。JPEG で使われるやつですね。で、the image will be transformed to the frequency side, domain side, and the time domain, and it returns to the domain, to time domain side by using the inverse DCT. わかりますよね。離散コサイン変換して逆離散コサイン変換すると何でしたっけ、時間空間から周波数空間にこう行って、で、JPEG なんかでやってるのは、フリケンシーだから何でしたっけ、周波数空間に持ってって、ここ半分に落とすんですよね。そうすると、人間の目ってバカだから、すごい高周波の部分ってよく分かってないんで、この高周波の部分全部落としてしまえば分かんないですね。というような圧縮をかけますよね。そうすると画像が半分になると。というようなやつをちょっとデモでやってみます。まあその式がこんな感じなんですね。で、これをだから IJ なんで、this is two-dimensional, right? So we just put each core in IJ. So in that case, we can very easy to program the easy to make the OpenCL programs like this. This is the DCT サイド。これ離散コサイン変換側ですね。だから F の IJ ってやつを、これ2-dimensional で we can get the get global ID. So 0 and 1, so 2-dimensional. Then we just get the numbers. Then just assign each IJ to the computing side. It's the same in the inverse side. 逆変換も同じです。逆変換も XY っていうのをこれ XY に与えてあげてやればいいと。まあこれあれですね。これは別に OpenCL のやつなんで全然エピファニー関係ないんですけど。で、エピファニーの方もまあ全然関係ないですね。全く同じです。It's the same, even if it is in Epiphany, because it's an OpenCL standard, so it's the same. Then just calling the program by using どれだっけcreate program どれだったっけ忘れちゃった。そうですね。create program with source。だからソースコードを与えて、source code will be given to this program. It will be compiled by using the CLCC. So I'll show later. So CLCC is the compiler from the Brown Deer. Then this is a command Q. It will be executed by command Q. Then I just show an example. はい。これでおしまいなんで、ちょっと待ってください。L の、なんだっけ、2DC。 これね、問題があってですね、性能が出ないんですよ。で、ぜひ見てほしい。2D でしょ。で、これレーナさんって知ってます？レーナさんね。レーナさんです。で、例えば、16×16 やりましょう。16×16 でも結構重いんですけど、This is 16 by 6, 16, DCT. As we have to see, this is the truth. So CPU side 0.03 second. We are waiting for the result from the Epiphany. Should we wait? A little bit more, I think. How can we understand this number? I don't know, but it works like this. So, but I think I'm very expecting the library will be upgraded. The parallelism will be effective in the near future, I think. So, the summary is I just showed the many core accelerator with mesh networks, that is Epiphany. The Epiphany is controlled by the ARM core, and we have to make 2 programs in the host side and the Epiphany side. And I show 2 kinds of programming environment。2つのやつ見せました。1つは ASDK っていうので、ハードワイヤードで作らなきゃいけないやつと、あとブラウンディールの、この、OpenCL ですね、というのを見せました。That's all. Thank you very much.
先生、ありがとうございます。じゃあ次は、アニシさんの方で、先ほどのオーストラリアの方ですね、ハイパフォーマンスコンピューティングウィズパラレラということで、